Welcome, everyone, to our course on production management. Over the span of these two modules, we'll explore the foundations, strategies, and tools that keep production systems running smoothly. Whether we're talking about a car manufacturing plant, a pharmaceutical production line, or a small bakery, the principles we'll discuss apply in some way to all production settings. The aim here is not just to memorize terms but to understand the logic behind production decisions, why certain processes are set up the way they are, how we measure success, and how to adapt when things don't go according to plan. We begin with factory physics, the science behind how production systems operate. 1. Factory physics. Factory physics is a framework for understanding the laws and principles that govern manufacturing systems. Just as physics explains the behavior of the physical world, factory physics explains how materials, information, and work move through a factory. It provides insights into performance limits, efficiency, and trade-offs. At its core, factory physics examines flow, how work moves from one process step to another. In any production system, we have three key elements. Inventory, items waiting to be processed. Throughput, the rate at which products are completed. Cycle time, the time it takes for an item to move from start to finish. One of the central ideas in factory physics is the recognition of inherent trade-offs. For example, increasing throughput may require holding more inventory, but that can increase storage cost and risks of obsolescence. Reducing cycle time may require investment in faster equipment or more workers, which raises cost. These trade-offs are not arbitrary, they follow predictable patterns that can be analyzed and optimized. Factory physics also looks at variability, differences in processing times, arrival rates, or machine reliability, which can disrupt smooth flow. Understanding these variations helps managers set realistic targets and design systems that can handle fluctuations. A well-managed factory is not about eliminating all variability, which is impossible, but about controlling it and buffering against its negative impacts. 2. Factory measurement and dynamics. If factory physics tells us the laws of manufacturing, factory measurements give us the metrics to track how well a system is performing. Without measurement, management is just guesswork. Key measurements in production management include cycle time, how long it takes for a unit to go through the entire process. Throughput, the number of units produced per unit of time. Work in process, WIP, the amount of partially completed work at any given time. Utilization, how much of a machine's or worker's available time is spent producing. Yield, the percentage of products that meet quality standards without rework. These measurements are interrelated. For example, if cycle time increases, throughput may decrease unless more resources are added. Similarly, high utilization may sound good, but if it's too high, it can cause bottlenecks and delays. Factory dynamics refers to how these measurements change over time and in response to adjustments. For instance, adding a second assembly line might double capacity, but only if upstream and downstream processes can handle the increased flow. Otherwise, the result might be excess WIP and congestion. Managers need to monitor measurements continuously, not just in periodic reviews, because small changes can quickly cascade into major performance shifts. Real-time dashboards, production control boards, and regular team check-ins are tools used to keep dynamics under control. 3. Variability. Variability is one of the most important challenges in production management. It refers to the differences in how work is processed, from machine breakdowns to inconsistent supplier deliveries to fluctuating customer orders. We can think of variability in two main types. Natural variability, caused by inherent differences in materials, human performance, or machine precision. Assignable variability, caused by specific, identifiable factors like a faulty machine, poor scheduling, or supplier delays. Why does variability matter? Because it can reduce efficiency, increase cost, and disrupt delivery schedules. For example, if a key component arrives late, the entire production line may have to stop, creating downtime cost and delivery delays. Managing variability involves reducing it where possible, better maintenance, better training, improved supplier relationships. Buffering against it where it can't be eliminated, holding safety stock, building extra lead time into schedules. Designing systems to be flexible enough to adapt when variability occurs. The goal is not perfection but resilience, the ability of the production system to keep running smoothly despite inevitable fluctuations. 4. Push and pull production systems. One of the most fundamental distinctions in production management is between push and pull systems. In a push system, production is based on forecast. Products are made in anticipation of demand and pushed through the system, often into inventory until customers order them. This approach can ensure products are available when needed but risks overproduction and excess inventory. In a pull system, production is triggered by actual customer demand. Work is only done when there is an order or signal from the next process step. This minimizes inventory and aligns production closely with demand, but can lead to delays if the system is not responsive enough. Many companies use a hybrid approach, pushing to a certain point in the supply chain, then pulling from there. For example, a manufacturer might produce standard components in advance, push, but assemble final product only when an order is placed, pull. In environmental terms, pull systems tend to be more resource efficient, as they reduce waste from overproduction. However, they require highly reliable processes and suppliers to respond quickly. 5. MRP and production planning. Material Requirements Planning (MRP) is a system used to ensure that the right materials are available at the right time for production. It works backward from the production schedule to calculate what materials and components are needed, and when they must be ordered. An MRP system requires 3 key inputs. A master production schedule, what products need to be made and when. A bill of materials, a list of all parts and materials needed for each product. Inventory records, what materials are currently available. MRP is a push-based planning tool. It schedules production and purchasing in advance based on forecast. It can be very effective in stable environments but less so when demand is highly unpredictable. Production planning goes beyond MRP to coordinate all aspects of the manufacturing process, including capacity, workforce, and supplier coordination. The objective is to meet customer demand efficiently while minimizing cost and waste. Advanced systems integrate MRP with Enterprise Resource Planning, ERP, which links production planning with finance, sales, and other business functions. 6. Capacity management. Capacity management is about ensuring the production system can meet demand without excessive delays or cost. Capacity is the maximum output a system can produce in a given time under normal operating conditions. There are different types of capacity to consider. Design capacity, the maximum output the system was built to produce. Effective capacity, the maximum output under normal conditions, accounting for maintenance, breaks, and minor disruptions. Actual output, what the system actually produces. Balancing capacity with demand is a constant challenge. Too much capacity means underutilized resources and higher fixed costs. Too little capacity means missed orders and frustrated customers. Strategies for managing capacity include adjusting workforce levels, hiring temporary staff during peak seasons, scheduling overtime or extra shifts during high demand, subcontracting certain work when in-house capacity is insufficient, investing in new equipment or technology to increase long-term capacity. The best capacity strategy depends on the predictability of demand, the flexibility of resources, and the cost structure of the business.